Alright guys, so let's talk about optical instruments. So what's the idea of an optical instrument? The basic objective of building an optical instrument is to be able to produce an image of an object that has an angular size, the image has an angular size bigger than the angular size that the object has when you look at it with your naked eye. That's the basic idea of an optical instrument. You always want to produce an image that is bigger than the image that you get when you just look at the object without any aid. So what is the magnification of the most basic optical instrument that we can construct? The most basic one is a convex lens, otherwise known as a converging lens. So a converging lens, as you know, has two focal points. The focal length is a positive number. All lenses have an optical axis, the axis that goes the axis of symmetry of the lens. And for a magnifying glass, in this discussion of a magnifying glass, we're going to assume that we're looking at an object that we have placed at the focal point. We're just going to bring the magnifying glass close to the object until the object is at the focal point of the magnifying glass, of the convex lens or converging lens. So if we do that, we've discussed this before, then the two of the principal libraries that we can draw is one of them goes through the center of the lens, that goes without any change. The principal library that goes parallel to the optical axis is sent to the focal point, and since the object is sitting at the focal point on the left, then the two libraries are going to become parallel. So what that means is that the image of this flower is going to be at infinity. That implies that we can focus on the image. When we're using the magnifying glass this way, we can focus on the image of the flower with a relaxed eye. That's because our eyes are designed to focus light that comes in parallel without any effort. No accommodation is necessary. No engagement of the ciliary muscles are necessary to focus an image of a faraway object. So when using a magnifying glass this way, we get an image of an object that is easy to look at for long periods of time. So this is the preferred setup when using a magnifying glass. So the question is then, what is the magnification of a magnifying glass, of a simple magnifying glass? That is, well, the first thing that we have to talk about is what is the angular size of an object, because what we're after is to produce an image that has an angular size bigger than the angular size that the object has when we're just looking at it with the naked eye. So looking at the flower without any magnifying glass, the flower would have an angular size that we're going to call theta np. Np is for near point. So the closest we can focus on an object, the closest to our eyes that we can focus on an object is 25 centimeters. So that obviously gives you the biggest angular size when looking at an object. If you want to look at the details of an object, you obviously want to bring it as close as you can to your eyes and still be able to focus on it. So the angular size for near point, or the angular size of the object without any aid, is h, the height of the object, divided by 25 centimeters. So this is the angle that we're going to compare to the angular size of when we're using the optical instrument. The angular size when using the optical instrument should be bigger than this number so that there is a magnification. So what is the angular size when using a magnifying glass? What is the angular size of the image that a magnifying glass produces? So let's go back to our sketch here, where the object is at the focal point and the image of the object is far away at infinity. The libraries that go through the lens are parallel to each other, and the angular size of the image clearly is the angle alpha that we have in this picture, and alpha is clearly h divided by f. The angle alpha that the image forms with the that a light ray that goes through the center of the lens forms with the optical axis alpha is the same as the angle here, and that angle is clearly in radians would be h divided by f, the height of the flower divided by the focal length of the magnifying glass that we're using. So now we need to compare this angular size of the image using the magnifying glass with the angular size with the naked eye. So the magnification of this simple optical instrument should be alpha divided by theta np. We have equations for alpha and for theta np, so we just have to replace. Alpha is h over f, theta np is h over 25, so canceling the h, we get that 25 centimeters over f is the magnification of a magnifying glass. So what that tells you is that if you use a converging lens with a focal length less than 25 centimeters, that is a magnifying glass. That's what we call a magnifying glass. You will have a magnification bigger than 1, which means the image will be bigger than just looking at the object with your naked eye. So for example, if you buy a lens that has a focal length of 10 centimeters, then the magnification of that lens, of the magnifying glass, will be 25 centimeters divided by 10 centimeters. That's a 2.5x lens. 2.5 is the magnification. The images that you see using the magnifying glass, provided that you put the object at the focal length, are going to be 2.5 times the size that you get when you just look at the object with your naked eye. Now, this is not the maximum magnification that you can get out of a magnifying glass. This is the 2.5x is the magnification when we put the object at the focal length. This is the standard magnification value because this is the most comfortable magnification when you place the object at the focal point, since the image is at infinity and therefore no accommodation of your eyes is necessary. So this is the standard value given for lenses. Now, a more complicated, slightly more complicated optical instrument is a telescope. What is the idea of a telescope? With any optical instrument, the idea is that you want to produce an image of a distant object. For a telescope, the object is always going to be very distant, like the moon, the stars, the planets, etc. You want to produce an image of a distant object which has an angular size bigger than the angular size that the object has when you just look at it with your naked eye. Again, that's the basic idea of an optical instrument. So we're going to, if we were looking at the moon just with our eye, then the moon would have an angular size that I'm calling here theta and e for naked eye. So the line of sight to the top of the moon and the line of sight to the bottom of the moon make an angle between them that is what we call the angular size of the moon. That's about ½ degree for the moon in the sky. So the basic idea of a telescope, of course, is to do better than that and have an image bigger than ½ degree in angular size. So to build a telescope, we're going to use a converging lens. This is one of the possibilities. Use a converging lens as the objective. The objective is the lens that is closest to the object, in this case the moon. So since the moon is very far away, we can consider it to be at infinity. Then you know that objects at infinity produce images at the focal point. Now, different parts of the moon are going to be focused at different locations, but they're all of the points, all of the light coming from the moon will be focused at what's called the focal plane. The top of the moon will be focused on the focal plane below the optical axis, and the bottom of the moon is going to be focused at the top, or above the optical axis on the focal plane. So this image that we're getting out of this intermediate image that we're getting out of the objective, what we're going to do is use a magnifying glass to look at that image. That is the basic principle of a telescope, to produce an image of a distant object inside the telescope, and then the eyepiece lens acts as a magnifying glass that looks at that image and produces a magnified image of it. So we're going to use a second lens, and as we discussed for magnifying glasses, the idea is to put the lens at a distance from the object that we're looking at that is equal to the focal length. So the eyepiece, which is this lens right here, has a focal length of FEP. So the idea is that the intermediate image of the moon, which is right here, should be located at a distance FEP from the eyepiece lens. So when we do that, we know that the image of the moon is going to be at infinity. The light rays coming from through this lens will be parallel to each other. The image is at infinity, as I said before, and it is upside down. If you notice that the intermediate image is upside down, then the final image is also going to be upside down, because the eyepiece doesn't invert. Working as a magnifying glass does not invert the intermediate image, so our final image would be inverted. So what is the magnification of the telescope? How much bigger is the size of the image compared to the image that, say, the moon has when we just look at it with our naked eye? So in this, just to simplify the sketch here, we have the moon, we have the objective lens, produces an intermediate image of the moon, then we have the eyepiece. The distance that the intermediate image is from the objective is equal to the focal length of the objective. We set up the eyepiece at a distance FEP, EP for eyepiece, FEP from the intermediate image. And when we do that, we know that the final image is going to be at infinity, and it's going to make an angle alpha with the optical axis. That's what we're going to call the angular size of the final image. How can we figure out that final angular size of the final image? First of all, notice that this theta NE is the angle, the angular size of the moon with the naked eye. So that's the angle indicated there. We're going to call the height, or the size of half of the moon from the optical axis to the bottom, we're going to call that h. And using this, we know that we can write that alpha is going to be h divided by FEP. Right, alpha, this angle alpha, this angle here is also alpha, and alpha is therefore the opposite side right here divided by the adjacent, which is right here. Okay, that angle is the angle alpha that we're talking about, the angular size of the final image. So the h, the height of the intermediate image, we can write it in terms of the angle theta NE. If you look at this triangle here, we see that theta NE should be h divided by f obj, the focal length of the objective. So theta NE is h divided by f obj, and we can use that and replace in the above equation. Instead of h, we can write theta NE f obj. So in the numerator we have that, and in the denominator we have FEP. And now we're ready to finally write what is the overall magnification of the telescope, because the magnification is the ratio between alpha and the angle with the naked eye. So when you divide alpha in this equation right here, when you divide by theta NE on both sides, you see that the magnification should be the focal length of the objective divided by the focal length of the eyepiece. The minus sign has been thrown in there because we know that the image is going to be inverted, because the intermediate image is always going to be inverted. So the final image is inverted compared to the real object. So this is the magnification for a telescope, for this setup of a telescope using two converging lenses. The other thing what this equation is actually telling us is that we can always build a telescope provided that we have two lenses, and if we're using converging lenses, then the focal length of the objective has to be bigger than the focal length of the eyepiece. If that is the case, then we can have a telescope that magnifies the image of an object. The idea, of course, would be to use the bigger focal length in front of the telescope. That has to be the objective, and the lens with the smaller focal length needs to be on the back. That's the place where we're going to put our eye. So that's why the telescope typically looks like this: a big front lens and a smaller lens on the back or on the side. The length of the telescope has to be, that we call in here L, has to be the focal length of the objective plus the focal length of the eyepiece. That was the setup that we just discussed. the object, the real object, the moon, the sun, the planets are at infinity, so the intermediate image is always formed a distance FOBJ from the objective lens, and the eyepiece has to be placed at a distance equal to the focal length of the eyepiece. So the sum of the two focal lengths is the total length of the telescope. So these are the basic equations that we have for a telescope: the magnification and the length of the telescope. Alright, if we, for example, have two converging lenses, one is 20 centimeters, the other one is 5 centimeters in focal length, then, as I said before, you can build a telescope with those two lenses. The magnification of the telescope and the length are given by the equations that we discussed before. So the magnification will be minus the focal length divided by the objective divided by the focal length of the eyepiece. As we said before, you want to use the bigger focal length as your objective, so the magnification will be minus 20 divided by 5, which gives you a telescope with a magnification of 4x. The length of the telescope, sum of the focal lengths of the lenses, so that's 20 plus 5 equals 25. So with these two lenses you can build your telescope by setting up the two lenses a distance of 25 centimeters from each other and using the 20 as the objective side of the telescope. Alright, finally, another very important optical instrument is a microscope. So very similar idea to the telescope. All optical instruments have the purpose of producing an image that has an angular size bigger than the size that the object has when you look at it with your naked eye. So it's the same principle. The only difference, of course, is that we're going to be looking at things that are not at infinity. We're not looking at far away objects with a microscope. We're looking at objects that are very close and very small. That's the only difference. So if we have a little bug or something that has a height h, the biggest angular size that object would have when we look at it with the naked eye would be when we place it at 25 centimeters. So the angular size of the object, as we said before, theta np, that's the angle at the near point of the eye, would be h divided by 25 centimeters. That's the angular size with the unaided eye. So this is the angular size that we are going to compare to once we get the angular size of the microscope. So microscope, again, basic idea, you're going to use a converging lens for the objective. Now the object is going to be close. The object cannot be at infinity, it's close to us, so we're going to place the object near the focal point of the objective. So the objective lens has a focal length, so we're going to place the object just a little further away but close to the focal point of the objective. So when we do that, we get an image of the object that is magnified. That is, the size of the image is bigger than the size of the object, because we know that when the ratio between the height of the image and the height of the object is given by the ratio between the distance to the image and the distance to the object. So that's clearly a number bigger than 1. So the first objective is magnifying. It's already magnifying the image of the object. And then the idea is to locate the eyepiece at a distance, or to look at the intermediate image, of the object with another converging lens, using it as a magnifying glass. So the eyepiece is going to be acting as a magnifying glass to look at the intermediate image that the objective is already magnifying. So that's the basic idea of the microscope. We're looking at, we're basically magnifying the objects twice. The objective and then the eyepiece both are magnifying the image of the object. So as discussed before, when using a magnifying glass, we want to produce the image at infinity, which means that the object is going to be placed at the focal point of the eyepiece. So if we do that, then the image of the little bug is going to be at infinity, and it's going to have an angular size that we're calling alpha here, the observer. when the person looks at the bug through the microscope, is going to see an angular size of alpha. So the length or the distance between the two lenses, or the length of the microscope, we're going to call it capital L. The distance between the intermediate image and the eyepiece is going to be the focal length of the eyepiece. The angle that the light ray that goes through the objective forms with the optical axis, we're going to call it theta. Okay, so in terms of this theta, we can figure out what is the angular size alpha of the final image. So let's call the height of the object h, the height of the image, we're going to call it h prime, and alpha is going to be the ratio between h prime, between h prime, okay, sorry, I lost track of this. Alpha, the angular size of the final image, is going to be h prime divided by the focal length of the eyepiece. So h prime is this one, the focal length of the eyepiece is this, so the ratio between the two is the angular size of the object. Now theta, the angle that we call here between the light ray that goes through the center of the objective and the optical axis, you can write it as h prime, the size of the intermediate image, divided by this distance, which, as you can see, is the total length of the microscope minus the focal length of the eyepiece. So h prime divided by L minus FEP is the that angle theta. So we can use theta in our equation for alpha. H prime can be replaced as L minus FEP times theta divided by FEP. Now theta can be expressed, as you can see inside the red circle. Theta can also be written as the actual size of the object divided by, remember that the object is close to the focal point of the objective, so h divided by FOBJ is the angle theta. So replacing theta with that number, h over FOBJ, then we are getting pretty close to the magnification. The angular size alpha of the image is going to be, if we replace h with the equation theta np times 25 centimeters, remember that the angular size at the near point, when we're not using the microscope, the angular size of the object is h divided by 25 centimeters, the near point. So we can write h as 25 multiplied by theta near point. So replacing that for h right here, we get this expression for alpha. Alpha is equal to that, and the last step, of course, is to divide by theta np, because the magnification of the microscope will be alpha divided by theta np. So doing that, and one final thing that we're doing here is to approximate the fact that the focal length of the eyepiece is typically very small, millimeters in the focal length. That's always very small, much smaller than the length of the microscope, which is typically 16 centimeters. So it is a good approximation to say that the L minus FEP is basically L. So the first term right here, without the focal length of the objective, can be approximated as L divided by FOBJ, and the second term here, the 25 divided by FOBJ, is right here. So basically the magnification can be written as the product of those two magnifications, the magnification of the objective and the magnification of the eyepiece. Okay, so the overall magnification of the microscope is the product with a minus sign, because one more time the image is inverted. So the magnification is minus magnification of the objective times the magnification of the eyepiece. So in a regular microscope that you might find in a lab, the eyepiece magnification would be labeled as, for example, 10x, The objective magnification would be also labeled. Let's say that it says 20x, and based on that information we could find what's the focal length of the objective, and also we could find what's the focal length of the eyepiece and the overall magnification of the microscope. So let's start with the first question. What's the focal length of the objective? So if the microscope says 20x for the at the location where the objective lenses are, then 20 is going to be equal to L divided by F OBJ. So L is the standard length of a microscope. All microscopes are built with a standard length of 16 centimeters. So we replace 16 centimeters and we divide by 20 to get a focal length of the objective of 0.8 centimeters. That's the same as 8 millimeters. Second question is, what's the focal length of the eyepiece? So for the eyepiece we don't have the same equation for its magnification. The equation for the magnification of the eyepiece is 25 centimeters divided by the focal length of the eyepiece. So that ratio is supposed to be 10 according to the label on the microscope. So 10 is 25 centimeters divided by the focal length of the eyepiece, and therefore the eyepiece is 25 divided by 10, which gives you 2.5 centimeters is the focal length of the eyepiece. What's the overall magnification of the telescope? The magnification is just a product of the magnification of the objective and the eyepiece. So 20 times 10 in this case gives us a total magnification of 200x. This microscope produces images that are 200 times bigger than what you would see if you just looked at the object with your naked eye. The focal lengths of the objectives and the eyepiece are given there using their corresponding equations. Alright, I hope that this helps you understand how optical lenses, optical instruments work, and in particular magnifying glass, telescope, and microscope. See you next time.